Hey everybody, thanks for coming. My name is Steve Hoffman, and joining me is Rick Fast. We worked on a microservices project at Orbitz together. That's what we're going to talk about today. I'm currently with Raise.com, and Rick is now with Expedia. Both great Chicago companies, both hiring. Check it out if you're in the market. So, Orbitz, the travel website. Started back in 2000 by the 5 major carriers as a one-stop shop for booking travel online. We're going to do a quick architecture overview history to kind of explain how we went from sort of a monolithic architecture to services and then finally to Microservices and Docker. A microservice talk isn't complete unless you talk about automated pipelines. Otherwise, you're going to be in a world of pain, and hopefully we'll have some time at the end for questions. All right, so like I said, Orbitz started back in 2000 by the major carriers. The architecture was pretty standard of the day. You had your web layer that served up your web, HTTP content, talked to a business layer, which communicated with the carriers. The website launched. It was basically a single application. We did on-demand releases by hand, and we were off and running. And basically what had happened was we had slapped a web facade on top of the system you see in this picture. There's actually a bunch of these. They're called GDSs, or Global Distribution Systems. These are those terminals you see the tellers typing in at the airport that you don't know what they're doing. A lot of cryptic commands, all those paper tickets, they've been replaced, those boxes of paper tickets, they've been replaced by electronic tickets, but effectively the systems are still the same. And so when we're talking about talking to the airlines through the business layer, we're really talking about communicating to a GDS. The first one that Orbitz hooked up to in 2000 was called WorldSpan, still around today. And in the 2003 timeframe, we hooked up to our second GDS, which was Sabre. Now, American Airlines actually uses Sabre, so if you booked an American airline ticket and we booked it in Sabre, it actually saved the airline money, and so that was the economics of it. American Airlines, around the same time, decided they wanted a consumer website, so we were happy to provide the connectivity. Northwest also got into the game, and we provided connectivity for them as well. And pretty soon we saw this architecture wasn't going to scale, right? So in the 2004 timeframe, we switched to a services model around a now defunct Java technology called Genie. And the idea was that each of these services would evolve independently. We'd have different release cycles, and everything would be great. And we kind of went along this line for a while. We hooked up more backends like Amadeus. Northwest merged with another carrier. American hooked up to Sabre directly. So they went away. Orbitz bought more brands like eBookers and Cheap Tickets. American Express needed connectivity. Not going to show you everything. A lot happened over the 15, 16 years of Orbitz history. But generally, the idea is that your system's always evolving, and so you need to evolve with it. So fast forward to 2015 when we started the microservices experiment. Orbitz had multiple brands, both websites and web services. So for instance, if you're familiar with like Kayak, they used XML web service that we provided to them. We connected to multiple backends. The entire system was comprised of over 500 separate applications running across thousands of instances in multiple data centers. And deployments were more or less daily. And then, of course, at the end of last year, Expedia came in and bought the lot. So, as you can imagine, applications that evolve organically over a decade tend to accrue a little bit of process. In 2010, Orbitz was doing 2 releases a year. You can imagine how well those releases went. I'll give you a hint, it was bad. By 2012, which is when this picture was taken, it was about 18 days from code to production. And what this picture was trying to, what they were trying to map out was all the steps necessary to get from code to production. And a lot of these were very, very manual steps. And so a lot of time was spent trying to eliminate as many manual steps as possible. They got it down to about 1 to 4 days. You also saw Conway's Law at play. This is where Development had their tool, which was a tool called Glue for deploying Java applications. Operations used CF Engine and then later Chef. And this kind of mismatch between the toolage sort of caused people to not create more services. So even though we had a service-oriented architecture, the pain involved was just, I guess, more than they could bear, and they just lumped more and more code in. And so 15 years later, we'd come full circle, and instead of having one monolithic application, we now had lots and lots of monolithic services. So one of these services Rick was working on, he came over to my desk and he said, hey, I've got this big application I want to break up, and I want to do a sort of 12-factor microservice architecture, and I want to use Docker. Can we run Docker? I said, I don't know. Let's see if we can figure it out. And so when we took this on, we decided, well, let's see if we can shave off all that human process, right? Let's find a way so that at some point human involvement stops and then it's just robots after. So we started with this box that we called the RickBot, right? We already had Chef in place, and the theory was that we would use Chef to deploy Docker, and then we'd launch our applications on top of this. But if you've ever used Docker, hopefully you have, it comes with certain challenges. For instance, if all three of these were the same service and they all listened on a particular port, they're gonna clash, right? And so Docker has this network translation layer so that everybody gets a random port. And so each of these services finding each other becomes a problem. You also have the problem of like logs, right? If your application is like logging the disk, it's actually logging inside the Docker container where nobody can get at it. So we needed to solve some of these problems. So the first thing we added to this picture was this box here. If you're not familiar with this, is console. It's a eventually consistent service registry from HashiCorp. We run this locally on every server that we run Docker images on. And the applications basically register and find other services via console. And when we launch the applications, we tell each application what its IP of the server it's on, as well as its external port. In this case, it's 31002, so that when it registers with console, everything can be found, right? To deal with the logging problem, we had just converted over to using an Elk stack, Elasticsearch, with Kibana. And so what we did was we dropped a Logstash agent on every box so that we basically bypassed the default logging and we used a network logger. Again, because we knew the IP of the machine we were on, we would just use a well-known port that we ran the Logstash agent on, and the Chef configured Logstash would forward it to the appropriate Elk cluster. And then, of course, you got to have metrics. Orbitz, you may or may not know, but Orbitz open sourced Graphite back in 2008. We have a lot of graphs. And so we followed the same pattern. What we did was we dropped a local agent on the box. There wasn't a relay for this. Rick wrote it. It's basically a little Go relay called Mr. Pickles that is configured by Chef to point to the appropriate Graphite cluster. And again, because we knew every Docker container knew its IP, it would basically connect to a well-known port, and then Chef would configure Mr. Pickles to forward it to the appropriate destination. Okay, so this works great, but if you were at Sam's talk or anything before, you know that you're going to have lots and lots of these boxes. You're not going to like SSH all over the place and type Docker run this, Docker run that. What you really want is you want something to manage your Docker containers across lots of machines. Luckily, around the same time that we came to this conclusion, Mesos had just announced support, first-class support for Docker. And so this is a picture from the Mesos website of their architecture. You basically run, you basically have a master, or hopefully multiple masters. They go through a zookeeper election, and then there's a bunch of slave nodes. They call them agents now. And on top of that, you run a scheduler, which then launches applications on the particular Mesos agents. In this case, we're really talking about using the Marathon scheduler. So our picture looks something like this. We run the Marathon scheduler, provides a UI and an API for us to communicate with. we find the master, the elected master through Zookeeper, and it manages the slaves. And this is where we'll launch Docker. So our picture now looks something more like this. Every one of these Rickbot boxes becomes a Mesos agent, and we use Marathon as the mechanism by which we communicate through to then launch the Docker containers on our behalf. Now, there are some applications where they're not console aware, and so they have to be discoverable via a name and a port. And for that, we used an open source project called Bamboo, which communicates with Marathon to basically rewrite its routing rules. So we have a static farm of HA proxy boxes behind a load balancer, and that's how the routing to the services happens at the edges. And so that's basically the setup, right? But the real magic really happens once you start stitching this environment along with other environments together in an automated pipeline. For that, we tried to use Jenkins, and hopefully with as little human involvement as possible. Rick's going to walk us through some of that.
Hello. So we had a pretty good use case for microservices, and that was in our SEO landing pages on Orbitz. They used to look like this. They actually don't look like this anymore. They're now powered by Expedia. But for the case of for this use case or this case study, we're going to talk about it from Orbitz about a year ago. And this is an Orbitz landing page. Ideally, if you Google Chicago hotels, this is close to the top. We strive to get it as close to the top as we can. If you Google Orbitz Chicago hotels, it will be at the top. And these pages are comprised of what we call modules. And these modules on the front end are just these little squares of content, and they come from different sources on the back end. And the application that they come from on the back end is this large monolithic service that I'm going to talk about. And I'll talk about a specific module in this talk, which is the editorial module. And the editorial module represents business user-contributed content, copy, and images. And it's retrieved from our CMS system on the back end, which was powered by Solar. So our architecture looked kind of like this. The actual Orbitz website on the front, and then our content orchestration service on the back end. We call it Flex, but for this talk, we'll just call it the content orchestration service. And so it's comprised of all these modules, and all these modules are basically implementations of a Java interface that will retrieve the data that's merged with the templates on the front end. And so they're all kind of generic. This is like a dynamic page building system, basically. And unfortunately, though, it crosses lots of the lines of business that we support at Orbitz, so hotels, search, content, air, all that stuff, cars. And so you've got a lot of teams because we're kind of organized based on mostly verticals. And so there's many data sources, there's many teams contributing. And this diagram only shows 3, but there's actually more like 40 modules and probably like 10 teams contributing. And so you can imagine the types of problems we have. Multiple teams stepping on each other's toes, dependency hell. There's a major lack of resiliency with everybody living in the same JVM. It's like, somebody can overuse thread pool, like, use a bunch of resources and basically ruin it for everybody. And so when you have all these teams contributing, it's easy for somebody to take down the whole stack. We looked into things like OSGI and modularization inside the JVM, but none of them really seemed to scale well and especially weren't dev-friendly. And also, the worst part was one release cadence. So the typical larger service at Orbitz, the deployment had to be scheduled, and typically it was weekly. Some applications were on the order of days. But each release typically contained a lot of commits from a lot of teams. And so what we decided to do, as you can imagine, is we split the modules out into separately deployable microservices. And the applications, we decided up front that we're going to rewrite our platform so that everything out of the box can kind of support the 12-factor principles, which we could probably do a whole other talk on. But really what this means is simple configuration, stateless, delivering your schema as code with your applications, quick startup, graceful shutdown, things like that. And all these services are just using HTTP with JSON or protocol buffers. But they're separate builds They're separate code repositories and even separate technologies if they needed to be. And so the teams end up looking more like this. So the hotel team has their module, the search team has their module, et cetera. And this allows the teams to manage their own deployments and releases. And really, it gives everybody kind of resiliency. Like the whole system can't come down from one of these guys because the content orchestration service is now just making API calls at these things, and we're using circuit breakers and timeouts to ensure that one module can't affect the page. So, when a module goes down, you might be on a landing page and you might miss some copy or like an image or something like that, but overall the page survived. And so the other nice thing about this architecture was we decided to peel off the back of this large service, and so the rest of the company doesn't know about this. We didn't have to boil the ocean to rebuild this. We can kind of just peel one module off at a time, and so it was completely transparent to everyone else. Anyway, before we decided to go continuous delivery, we had a process that looked kind of like this, and so our builds were mostly triggered by check-in, but some were on-demand only. But the worst part was really that we built the same code numerous times. And so we called them betas, you might call them snapshots, and this makes sense for like libraries and stuff, but when you're talking about your services, we really want every build to be, it doesn't necessarily have to go to production, but we want it to be able to if it wanted to, or if we wanted it to. And so the way we were doing it was we were building, testing, discarding, building, testing, discarded, and then it's Tuesday and we want to release, so we call it 1.2, and then we build it and we test it and we deploy it, and at this point it's got 20 commits in it, and if something is broken, it's a little harder to know what changed. And so in the new world, we want every build to be a release candidate, which is why we implemented continuous delivery with Jenkins, Docker, Ansible, and Marathon. But first, we want people to create new apps when appropriate. We don't want people to keep tagging on things that don't fit on existing services, which is a problem that we had. So we wanted to make it cheaper to create new services. And so this is the second time we've seen this picture today, actually. We used Yeoman. It's a JavaScript library for scaffolding projects. Basically, you just create a bunch of templates. It's usually used for things more in the front end ecosystem, but it works fine for us. We were building Java Gradle projects, and so it basically would give us a skeleton project with all of our kind of chassis libraries baked in as dependencies. So it also would do things like prompt you, like, did you want to connect to Solar? Did you want to connect to a certain database? And you could basically pre-configure some of your wirings in. And then the code base is obviously generated, and then we push it to a Git repo. And at Orbitz, we use Stash for that. And one of the nice things about Stash was that we could build in kind of a gate at the beginning. And we didn't want gates, but we needed something to, so we weren't just winging stuff into production willy-nilly. And so we do that through the pull request. And we use a plugin called the Work Zone plugin for Stash, which basically protects master. And it makes it so we can't just merge our code. It means we have to make a pull request with a minimum number of reviewers. So the committer here, he's made the pull request, and you can see he can't merge. And the reviewer can't merge either, but he can review the code and approve it. And then once he does that, we have a bot that can actually merge. And so he's the only guy that can get our stuff to master. And then once that happens, the Jenkins Stash commit hook is triggered, and then that's the last thing that humans do in our pipeline, unless we explicitly configure a button later on, but I'll talk about that in a little bit. So the Stash commit hook triggers the Jenkins pipeline, and our first cut at the pipeline had 4 step types, and they were just Jenkins jobs built using the job DSL plugin, which kind of is a way to template out Jenkins jobs so that you're not like creating them through a UI, which obviously wasn't going to scale for the number of services we were building. And we had 4 step types. There was the build and push, which would actually compile and build your artifact and push it to some artifact repo. We have the deployment step, acceptance tests, and then our paper trail, which is change ticket creation and updates. And I'll talk about all these in just a second. And this is a simplified view of what our pipelines would look like. We had over like 20 environments. We did a lot of stuff in parallel. We had lots of partners that required us to be in separate environments. For example, like American Express, stuff like that. They needed their own stack. So we ended up with a lot of environments, and so we wanted our pipeline to be able to do that fast and also in parallel. And so ultimately, we build the application. The application name and the version are really the only two pieces of information the rest of the pipeline needs. So we'll talk about the steps now. The Jenkins pipeline build job pulls the latest from master, builds and runs our unit tests. In our case, most of these services were Spring Boot applications built with Gradle. And so our first use case was let's just support Gradle. And so we do the Gradle build. Our Gradle configuration file says, hey, this is version 1.2. Now we say it's 1.2, but that's not what we're actually going to publish. We use the Jenkins build number to create a unique release candidate version, right? So we built the jar, and then we interpolate that value, which is, say, this is the 17th build. So now we have this unique version number, and it's a nice-looking version number, so we know what order it was deployed in. So we know that 1.2.18 is a newer version. You'll see a lot of people using things like git commit hashes, which simplifies this process, but it also makes it so you don't know if it's a newer version or an older version. Anyway, so normally we would take our war file or jar file and push it to Nexus or Artifactory or one of those types of artifact repos. But what we do next actually is we build a Docker image. And so we use the Gradle integration with Docker to do that. In retrospect, after we started having different types of builds, I wish we hadn't, but we did. But essentially, we had a very simple Docker file which used our base Orbitz Java 8 image. And then we'd copy this newly built artifact into the image, set the working directory, and then set a simple entry point. And so now we have a Docker image, and we tag it with our unique release version. So 1.2.17, that's our Docker image tag. And it's ready to get pushed. We used to push them to Docker Hub, but we actually owned Artifactory, and it has actually very nice Docker registry. And so we push our versioned artifact here. And so the rest of the pipeline is going to pull this image by this tag from Artifactory. And so the rest of the pipeline can access it. Deploy step. This changed significantly as we worked on it. And our first shot was really, let's just use Docker. That's what we just wanted to deploy with Docker, and Java deployments have been kind of pain in my ass for my career, and so this was nice. It was nice that I could just push them out there, and it was pretty reliable and a very simple deployment. We used a tool called Ansible, which is a configuration management tool that's good for rolling across hosts and executing remote commands. It has a nice Docker module, and so we used that first. And what this did, you can see here in this picture, is relying on like a fixed inventory of hosts. It rolls through, shuts down the old version, launches our new version, in this case 1.2.17, waits for the health endpoint to come online. We'll talk about that in a minute. And then once everything's good, we shut down the old one, we move to the next host. We're doing this in serial. Kind of took a while, but I was happy. We did a Docker deployment. But there was a ton of problems. And we knew there were going to be problems, and we felt them soon. Failures are kind of weird. Part of a single environment could fail. The whole environment could fail. Do you roll back just that host? Do you roll back the whole environment? Do you try to retry? We're doing this with YAML files. Just recently, I think they added kind of try-catch semantics in Ansible. But ultimately, it was a bunch of logic that we didn't really want to own. And also, we're just running Docker. Sam mentioned this earlier with things like Docker Swarm. It's not fully supervising your containers after they run. So we're deploying these things in a cloud environment where guys will shut down VMs because they have to move them to another physical host. When Docker comes back up, it doesn't know what it was running because it's a new Docker. And so we noticed like microservice instances just disappearing here and there. Also, we're deploying to a fixed number of hosts, and so once we fill those hosts up, then we have to create another pool, and that would make things a lot more complicated. And so, the clear answer here is we need to use a scheduler. And so we decided to try something new. We stuck with Ansible because I think it's a nice tool for doing deployments. We built our own Ansible module that would do a marathon deploy, and I think, and this was a couple years ago. I think nowadays there's probably a open source one available for Ansible. I know there's one for Terraform. But essentially, we can just give it the image name with our release version, number of instances, and some configuration, and then Marathon can handle all the complexity for us. And so this is my picture of the RickBot server image that Steve showed earlier, and we just added one new kind of local helper service, which is the Mesos agent. And so this allows us to participate in the Mesos cluster and allows us to use Marathon to do deployments. So same deal, our Jenkins deploy job pulls the Ansible playbook, but this time the playbook doesn't care about a rolling set of a set of hosts. It just cares about where Marathon is. And so Marathon's just an HTTP API that we can interact with. And if you think about it as if our whole cluster of Mesos agents as a single computer, you can think of Marathon as initd. And it's just a simple HTTP API. And so our playbook really just calls that with a configuration. One thing to note, though, is that Marathon is asynchronous. So when you send it JSON, it says, OK, I got it, thanks, and it returns. And so we have to manage that ourselves. Otherwise, our pipeline's going to end before the first environment even finished deploying or failing. So we end up with something like this. This is weird HTTP pseudocode. But essentially, our playbook checks to see if it exists, the application itself. If it doesn't, then we do a post with a JSON document specifying the image, configuration, things like that, mostly Docker related. If it does exist, then we do a put, pretty much with the same configuration, and then we get a deployment ID back, and then we have to pull this deployment endpoint until that disappears, and that's how we know that it was successful. I wish there was a better way, but at least then there wasn't, and then we basically set a timeout. So if it takes longer than 2 minutes, then it probably failed, and so the Ansible module itself will then return. But basically, we use the Ansible module to make it seam blocking to the rest of the pipeline so that the pipeline doesn't keep going. One other piece of our Marathon configuration that I think is important is we have different types of configuration that we deal with at work. A lot of the configuration that we used to deal with at Orbitz, like our metrics, our logging, service discovery, stuff like that, was stuff we had to tell each application through configuration files. That's baked into the infrastructure now, and so Chef manages that for us when it stands up our RickBot agents, right? But there are things that individual applications care about, like their databases or some other value, right? Things that are environment specific and application specific, we allow developers to specify in a file in their source repo with the application, and those are injected when we do the deployment as environment variables. And we have a different way of managing secrets, which I'm not going to get to today, unfortunately. So after we make the calls to Marathon, it interacts with Mesos, getting resource offers to find out where to place our stuff. I only had room for 3 servers here, so it's pretty obvious where they're going to get placed. But Marathon starts up the new version, right? So we've got the Docker image at 1.2.16 running in blue, 1.2.17 running in green. It does it in parallel this time, which makes our deployments a lot faster, which is nice. It does require you to have extra capacity to support having 2 of everything for a short period during the deployment. All of our applications have health endpoints. Probably if you're using Spring Boot or Drop Wizard or something at this point, you probably do too. That's a first-class thing in Marathon. And so when we post our JSON or put our JSON to Marathon, we tell it about our health check endpoints, and it continues watching those during the deployment and even afterwards. And so all of our guys are okay. We're at 200. And so then we gracefully shut down and destroy our old version. And the graceful part is the important part here. The first time we started playing with this, we were just killing stuff, and we were getting failures because connections couldn't drain. And more importantly, using service discovery like console, we're registering and deregistering application instances. And when we kill them, they don't get a chance to do that. And so that was a mess. But once we got a grip on our signals, worked pretty well. And so that was one environment, and now we're off to the next environment. So 1.2.17 is deployed here, and we'll just keep going through our pipeline and doing the same thing. But the nice thing about Marathon, and this is really the key for any scheduler, Kubernetes will do this for you. I guess newer versions of Docker Swarm will do this for you. ECS and Marathon, they're continually polling your configuration. So they know how many instances of everything you need. They know the health check-in points, and so they'll keep track of things. Single instance goes bad, disappears, or if the health check's returning like a 503 or something, it knows that it needs to start up a new one, and it'll do that for you. Also, in this case, if the whole node goes down, then Marathon's still watching, and this is kind of a dumb case because it's going to have to co-locate them because I've only got 2 squares left. But it's going to go out, talk to Mesos again, and find a new place to put the resource. And it found a place. We check the health endpoint again. We're at 200, and we're back at capacity. And that's huge. I mean, that's the reason to use a scheduler, I think. I mean, the API is nice. It makes it easy to write resilient systems. The next step type is kind of a more loose step type is our smoke and acceptance testing step. Teams did this differently depending on the type of application it was. We always encourage people to do unit testing kind of embedded at the build time as much as you could to get the coverage there. But as you go through the pipeline, you might do different types of functional testing or black box testing. A lot of teams would actually use our service discovery mechanism console to just do like basic tests across a whole cluster, but not testing like really deep functionality, but just, is this thing working? And a lot of teams now will even do a canary deploy to production, run tests against that, and then once that's good, then they'll deploy the actual application that's taking real traffic afterwards. But we made that configurable. And then finally is the paper trail. All of our deployments, the scheduled ones, legacy deployments, and these deployments require change tickets in a product called ServiceNow. I'm sure some of you have used it. It's a ticketing system. It's very configurable. We configured it heavily. But essentially, these steps we bookend our production deployments with, and what they do is they pull information from Jira and Stash to create all the information about this ticket. And they create a ticket in ServiceNow. If the Marathon deployment fails, then we close it and mark it as failed. And if it's successful, we close it successfully. And the nice thing here is that it's completely transparent to our release managers and to operations. And so when you put it all together, you get something like this. And after this pipeline's run, our new version of the editorial modules in production, all of our paperwork's are complete, and we're ready for the next commit. And so if you build it, they will come. We built this for a small part of the Orbitz website, but once we started delivering things to production in 10 minutes, other people wanted to start doing this, and so we had to scale it out to other people, not just for other applications, but we quickly found that managing Jenkins jobs is unwieldy, even if we're using the jobs DSL stuff. We're changing pipelines a lot. Teams want to reconfigure their pipelines, and we found that managing them as jobs was hard, and we couldn't represent that as code until we started using a plugin called the Workflow plugin, which I believe is now called the Pipeline plugin with Jenkins 2. And what that allowed us to do was configure Jenkins jobs using a Groovy DSL. And you can see an example here is specifying a Jenkins job that pulls the editorial module, runs the Gradle build, and then it has the support for Docker, which is building our dynamically versioned Docker image. And then you can see here that we're pulling our playbook and running our Ansible playbook to do the deploy. This is still a static pipeline, and we didn't want everybody to have to specify this either, because we don't want 50 to 100 teams with microservices having to write Groovy code to manage their pipelines. And so we took it a step further, and we said, we want something like this. So think about like a Travis build or something like that. Having a nice little document that specifies your build, and even in our case, specifies our build and deployment and other types of steps to run in serial and in parallel at certain points. And so we have this pipeline.json file that teams automatically have at the root of their generated microservice code. And it specifies things at a higher level. So here we're saying Gradle build, which is the build step I talked about, and then you can see below Marathon deploy into the test environment. We also allowed them to specify things like environment variables in this file so they could kind of configure everything about their application deployment and configuration all in one place. And so then our workflow became a lot more complicated, but there was only one of them, and it was kind of managed centrally so that we could kind of standardize on the way the different type of steps worked. And so this was nice. It just became a little grosser looking in the fact that we had to parse in the JSON and then iterate through the steps and then dynamically call these Jenkins jobs. But ultimately allowed the teams to deploy whatever environments they wanted, and if they wanted to create a new step type, we would just have to add a little snippet to the central pipeline. And so lots of teams started getting on board, and we started going a little more polyglot than we had expected, and so people wanted to start building Python apps and Go apps and stuff like that. And so we decided we needed to even take our Jenkins setup a little further, which Steve's going to talk about right now.
So as you can imagine, just like our code, our Jenkins environment had also sort of evolved or devolved over time. We had sort of a standard setup where you set up Jenkins, you set up a bunch of slaves, and then over time, you start adding version after version of all the various tools. So you'll have 6 versions of this and 10 versions of that, and then you have compatibility issues, and it gets pretty messy pretty fast. Not to mention the building of our monolithic application was so destructive to the slave that they had built some custom, take a snapshot of the Jenkins slave, run the build, and then run this script to take it back to its previous state. It was horrible. And so it looks something like this. You check out you check your code in, it builds to a slave, and then you run your little time machine script. This was terrible because it meant that every slave could only be used for one thing, right? So it didn't matter how big or small your build was, you got the same thing. And so we wanted more flexibility. Luckily, someone had done some nice Jenkins Mesos integration via this plugin. And so the setup became something more along the lines of this, where when you did your commit, it would, instead of just scheduling it straight to a slave, it would communicate with Mesos to spin up a dynamic slave, which was actually a Docker image. In a lot of ways, a kind of Jenkins microservice. And so we had a specific constraint set up for Mesos slaves that were for doing Jenkins builds, like you see here, this env, and the build just proceeded as normal. And then when we were done, basically we could just nuke the slave, and we got the same thing with sort of single-use slaves, and so we were able to just kind of build upon this. So when it came to doing a deployment, we created another kind of slave, which would check out a playbook and run it against a particular Jenkins slave that had Ansible and the Marathon libraries and everything installed. It would communicate with Marathon. It would then deploy to a separate Mesos slave, in this case the CI environment, and this was all done via Mesos constraints and parameters of Marathon. And again, when it was done, we would just nuke that slave, and the capacity is ready for the next thing. Once you do that, you start basically scaling out your Mesos infrastructure across network segmentation lines or access control. In this case, we got 3 pre-production environments. We got a little Jenkins environment off on the side, and that kept our builds from trashing other environments. We could also have different access controls for production and things like that. And then you keep scaling it out even further across multiple data centers or availability zones, and Jenkins then becomes this orchestrator across all these different lines. And so hopefully, to wrap up, hopefully you see that we haven't really talked a lot about the microservice aspect of it, but really more around the toolage that's really around it, right? We learned over a very long period of time that most of the time you spend in dealing with lots of applications across lots of machines is the process. And anything that you can do upfront to streamline it, figure out what process you want and work backwards from that. And investing that time early on will pay for itself, believe me. You want to have repeatable builds, repeatable deployments. You don't want to be part of it, trust me. If you're successful with your one app, it's going to take a while to get the first app going. But if you're successful, you have lots of apps, and then it won't be that much more work for you.